Welcome. Today we are diving deep into the mechanics of order. Specifically, we will analyze selection sort not just as a piece of code, but as a crucial study in the incremental approach to algorithm design. We will explore why a seemingly slow quadratic algorithm remains a critical tool for modern hardware engineers dealing with write-sensitive memory like flash and EEPROM. Let us begin by establishing the theoretical framework of sorting and where our subject fits within the broader taxonomy of elementary algorithms. At its core, sorting is a permutation problem. Given an input sequence A, our goal is to find a specific rearrangement, A prime, such that every element is less than or equal to the one that follows it. We are essentially transforming a state of entropy, or disorder, into a state of monotonic order, which is the prerequisite for efficient operations like binary search. Most general-purpose algorithms operate under the comparison model. Information theory tells us that to sort n elements, we must distinguish between n factorial possible permutations. This creates a theoretical lower bound on performance. While efficient algorithms hit the big omega of n log n bound, elementary algorithms like selection sort operate in quadratic time, yet they offer distinct mechanical advantages we will discuss shortly. When we look at elementary quadratic algorithms, we see a spectrum of trade-offs. Bubble sort is notorious for excessive swapping. Insertion sort is excellent for nearly sorted data but requires massive data shifting. Selection sort occupies a unique niche. It minimizes memory writes. It is deterministic, in place, and, as we will see, highly specific in its utility. To understand how selection sort functions, we must contrast the divide and conquer paradigm with the incremental approach. The incremental approach is constructive. Rather than breaking the problem into sub-problems recursively, we build the solution one step at a time. The algorithm maintains a strict loop invariant. At any step I, the subarray from 0 to I-1 is sorted. We proceed by expanding this ordered territory until it encompasses the entire dataset. Both insertion and selection sort are incremental, but their philosophies differ fundamentally. Insertion sort asks, where does this next element belong, and shifts data to make room. Selection sort asks, which element belongs next, and finds the global minimum. Crucially, selection sort places an element into its final position immediately, whereas insertion sort might move an element many times. The mechanics of selection sort can be visualized as a three-step cycle. First, we scan the entire unsorted partition to identify the absolute minimum value. Second, we swap that minimum with the element at the current boundary. Finally, we advance the boundary, effectively locking that element into the sorted history. We repeat this until the unsorted pool is empty. Here is the standard iterative implementation in C++. Note the nested loops. The outer loop tracks the boundary of the sorted region. The inner loop scans for the minimum. A critical optimization for memory-aware systems is the check if min IDEX not I. This prevents a self-swap, ensuring we only write to memory when absolutely necessary. Additionally, note that we use std.swap, passing elements by reference, rather than C-style pointers. Now we move to the rigorous mathematical analysis of the algorithm's performance, looking at time, space, and the critical metric of memory writes. Selection sort is often criticized for its inability to adapt. Whether the list is random or sorted, it performs the same work. The total number of comparisons forms an arithmetic series, summing from 1 to n-1. This results in exactly n times n-1 divided by 2 comparisons. Consequently, the time complexity is big theta of n squared for all cases, best, worst, and average. However, here is the redeeming quality. While comparisons are quadratic, memory writes are linear, or big O of n. In the worst case, we perform n-1 swaps.
Since a swap involves 3 assignments, the total write operations are bounded by 3n. This is drastically lower than insertion or bubble sort, which can perform quadratic writes. If we place this on a spectrum of write intensity, selection sort sits near the theoretical optimum. Cycle sort represents the absolute minimum, performing at most 1 write per element, but it is complex to implement. Selection sort offers a practical linear write complexity, far superior to merge sort's copying overhead or insertion sort's cascading shifts. Why does write complexity matter? In modern cloud computing, it often doesn't. But in the world of embedded systems and non-volatile memory, it is a matter of physical survival. Technologies like flash memory and EEPROM are not immortal. Every time we write a bit, we degrade the oxide layer of the floating gate transistor. These devices have a limited number of program/erase cycles, often between 10,000 and 100,000. Furthermore, writing is slow and energy-intensive compared to reading. In this context, selection sort acts as a powerful write minimization strategy. It is important to distinguish this from wear leveling, which physically distributes writes across the drive. Selection sort simply reduces the total volume of destructive operations. By offloading the burden to the CPU via read-heavy comparisons and conserving the memory controller via minimal writes, we significantly extend the lifespan of the hardware. Before we conclude, we must address the algorithmic behavior regarding duplicate keys and look at how this logic evolves. One major drawback is instability. Selection sort does not preserve the relative order of equal elements. Consider an array with 2 2s and a 1. The first swap will move the 1 to the front, sending the first 2 to the back, effectively reversing the order of the 2s. This makes it unsuitable for multi-key sorting workflows. The concept extends beyond the basic algorithm. Cocktail selection sort finds both the minimum and maximum in a single pass. Bingo sort is adaptive for duplicates. And most importantly, heap sort is essentially an efficient selection sort that uses a binary heap to find the minimum in logarithmic time rather than linear time. In conclusion, selection sort is more than just a classroom example. While inefficient for general sorting on PCs, it is a specialized instrument for embedded engineering. It teaches us that efficiency is not a single number. It is a trade-off between time, space, and physical hardware endurance.